All right, welcome back to the deep dive. So you've given us chapter 6 from a first-year chemistry text. We're ready to get into it. We've already sort of laid the groundwork in previous deep dives based on your materials, looked at atoms, the periodic table, chemical bonds, even molecular shapes. But, molecules don't just hang out alone in the real world, do they? They're always interacting, bumping, sticking, flowing. How they act together is what gives us solids, liquids, and gases. So that's our mission today.
Oh,
Go beyond single molecules. Understand these states of matter, solid, liquid, gas,
right.
what makes them tick, and what are these forces between molecules holding them together or not?
Exactly. It's a crucial step. We talk a lot about bonds inside molecules, but these forces between them, they explain so much of what we actually see. Why water boils where it does, why oil is viscous. It's not usually about breaking the molecules themselves apart. It's about the interactions among them. And these forces, even though they seem small, have, well, huge consequences.
Okay. Let's start simple. Solid, liquid, gas. Everyone knows those. If you picture water, ice, liquid water, steam, what's the fundamental difference down at the particle level based on the chapter?
It really boils down to how the particles are arranged and how much kinetic energy they have. So in a solid, the chapter says particles are packed very tightly, often in a regular pattern. They're basically vibrating in place, not really moving around each other. They have pretty low kinetic energy. That's why solids have a definite shape and volume.
Right, locked in place.
Then in a liquid, the particles are still pretty close, but they've got more kinetic energy, enough to slide past each other. Think of them kind of tumbling around. So a liquid takes the shape of its container, but the volume stays fixed because they're still mostly touching.
Okay, flowing but still packed. Makes sense.
And then gas, well, gas particles are way far apart. Lots of empty space. They have really high kinetic energy, just zipping around randomly, bouncing off things. So a gas just expands to fill whatever container it's in. No fixed shape, no fixed volume.
The chapter mentions other states too, right? Plasma, Bose-Einstein condensates.
Yeah.
Cool stuff, but maybe beyond our scope for today.
Yeah, fascinating areas. But sticking to the classic three, solid, liquid, gas, is key for this foundational understanding.
And things change between these states, obviously. Melting, boiling.
Right, phase changes. And these are all about energy. Going from solid to liquid or liquid to gas, you have to put energy in to overcome those forces holding particles together. That's endothermic. Going the other way, gas to liquid, liquid to solid energy is released. That's exothermic. It's always about balancing the energy against those intermolecular attractions.
I like the idea of picturing that simulation the chapter mentions. Seeing the particles like locked rigid in ice, flowing around in water, bouncing wildly in steam. It helps make it concrete. Okay, let's dive into gases first then. They seem the most, straightforward because the particles are so far apart.
In many ways, yes. Because they're so spread out, those intermolecular forces we mention are mostly negligible. Their behavior depends largely on four key things: pressure, P, volume, V, the amount of gas, usually in moles, N, and temperature, T.
And pressure. The chapter defines that as the force from the gas particles hitting the container wall, right?
Exactly. All those collisions add up. We experience atmospheric pressure from the air around us.
And the chapter lists a bunch of units at rem, mmHg, torr, kPa. Useful to know that 1 atmosphere is about 760 millimeters of mercury, or about 101 kilopascals.
Absolutely. And when you start fixing some of those variables, P, V, and T, you find these really neat relationships. The simple gas laws, like Boyle's law, keep the amount of gas and the temperature constant, and pressure and volume are inversely related.
Squeeze it harder, volume gets smaller.
Precisely. Then there's Charles's law. Keep the amount and pressure constant, and volume is directly proportional to temperature.
Heat it up, it expands, like the balloon example in the chapter. Shrinking in liquid nitrogen, puffing up when warm.
That's the one, a perfect visual for Charles's law. And finally, Avogadro's law. Keep pressure and temperature constant, and volume is directly proportional to the number of moles.
More gas, more volume. Simple enough.
And a key point there, equal moles of any ideal gas take up the same volume at the same temperature and pressure. It doesn't matter if it's helium or nitrogen or whatever.
Okay, so Boyle. P inversely to V Charles. V proportional to T Avogadro. V proportional to N. How do we tie them all together? Is there like a master equation?
There is. That's the ideal gas law. PV equals nRT.
The famous one.
It combines all those relationships. R is the gas constant. Its value depends on the units you use for pressure and volume. The chapter gives 0.0821 L at mol/K and 8.314 G/K as common ones. But the crucial, absolutely critical thing, temperature T must be in Kelvin. Always. No Celsius or Fahrenheit here.
Like Kelvin. Got it. The chapter shows an example like calculating moles of N euros in a container at STP standard temperature and pressure. which it defines as 1 atom M and 0 degrees C. So you'd use 273.15 Kelvin for T, plug in P, V, R sol for N. Pretty neat.
Mm-hmm. And it shows how you can double-check using the molar volume at STP that 1 mole of gas is about 22.4 liters. Divide your volume by 22.4 lamole, you should get basically the same answer for moles. It works out. The ideal gas law also lets you connect things like molar mass and density. The equation is D exist P molar mass RT.
Oh, interesting. So if you measure a gas's density under known conditions.
You can figure out its molar mass, which can help you identify the gas. The chapter walks through calculating that too. Very practical stuff.
Okay, that's for single gas.
Yeah.
But what about mixtures? Like air, it's mostly nitrogen and oxygen plus other bits. How does that work?
Good question. That brings us to Dalton's law of partial pressures. It's actually quite straightforward. The total pressure of a gas mixture is just the sum of the pressures each individual gas would exert if it were alone in that container.
Ah, the partial pressures.
Exactly. Each gas acts pretty much independently because they're so far apart. The partial pressure of one gas, say gas A, is its mole fraction, moles of A divided by total moles times the total pressure.
So PA, mole fraction of A total.
Precisely. The helium-hydrogen example in the chapter demonstrates that calculation nicely. You just figure out the fraction of each gas and multiply by the total pressure.
Okay, that makes sense. They're not really interfering with each other. What about how they move? You mentioned they're zipping around. How does mixing happen, like smelling something across a room?
Right, that's diffusion, the spontaneous mixing of gases because of their random motion. There's also effusion, which is a gas escaping through a tiny pinhole into a vacuum. Both depend on how fast the particles are moving. And that speed relates to their mass.
Lighter things move faster.
Generally, yes. Graham's law of effusion states that the rate of effusion is inversely proportional to the square root of the molar mass. So lighter gases effuse and diffuse faster than heavier gases at the same temperature.
The chapter had that cool demo idea, right? Ammonia and HCl gas from opposite ends of a tube.
Yeah. Ammonia, NHS, is much lighter than hydrogen chloride, HEl. So the ammonia travels faster down the tube. Where they meet, they react to form a white ring of ammonium chloride, NaHElO. And that ring forms closer to the HCl end because the lighter, faster ammonia covered more distance. It's a great visual for Graham's law. Lighter means faster.
Okay, so gases spread out, high energy, simple laws mostly rule. Forces between them are kind of negligible.
Yeah.
But now, liquids and solids, they're packed together. Those forces must suddenly be a huge deal.
They become the dominant factor, and this is a really key concept from the chapter. When you melt ice or boil water, you are overcoming the forces between the H2O molecules. You are not breaking the OH covalent bonds within the molecules. Those stay intact. The change of state is all about intermolecular forces, IMFs.
Intermeeting between, not intrameeting within. Got it.
Exactly. And the strength of these IMFs determines things like melting points and boiling points. Stronger IMFs mean the molecules cling together more tightly.
So you need more energy, higher temperature to pull them apart into a liquid or gas. Makes sense?
Right. The chapter details the main types. First, dispersion forces. These are present in all molecules, polar or not. They happen because electrons are always moving. Sometimes, just by chance, more electrons are on one side of a molecule than the other. This creates a temporary, instantaneous dipole. This temporary dipole can then induce a dipole in a neighboring molecule, leading to a weak, fleeting attraction.
Okay, like a temporary stickiness.
Sort of. The strength depends on how easily the electron cloud gets distorted. That's called polarizability. Bigger molecules with more electrons are more polarizable, so they generally have stronger dispersion forces. Long chain-like molecules also tend to have stronger dispersion forces than compact spherical ones of similar mass.
So bigger molecules, you get stronger dispersion forces generally?
Generally, yes. Second type, dipole-dipole forces. These only happen between polar molecules, ones with a permanent positive end and a permanent negative end, due to differences in electronegativity within the molecule. The positive end of one molecule is attracted to the negative end of its neighbor. It's like tiny magnets attracting each other, but weaker than a full ionic bond. The strength depends on how polar the molecule is, its dipole moment.
Okay, so nonpolar molecules only have dispersion. Polar molecules have both dispersion and dipole-dipole.
Correct. And then there's a special, extra strong type of dipole interaction, hydrogen bonding. This occurs when hydrogen is directly bonded to a very electronegative atom, specifically nitrogen N, oxygen O, or fluorine F. Because N, O, or F pulls the bonding electrons so strongly, the hydrogen atom becomes very partially positive, almost like a bare proton sticking out. This very positive hydrogen is then strongly attracted to a lone pair of electrons on an N, O, or F atom on a neighboring molecule.
Oh, so it's H bonded to NOS, attracted to another NOS.
That's the key. It's much stronger than typical dipole forces.
The chapter's graph showing boiling points really drove this home for me. Normally, boiling points go up with molar mass down a group because of stronger dispersion forces. But then, wham, water. Ammonia, NH, hydrogen fluoride, HHF. Their boiling points are way, way higher than you'd expect from that trend.
Exactly. That huge jump is entirely due to hydrogen bonding. Water's hydrogen bonds are particularly strong and extensive, which is why it has such a remarkably high boiling point for its small size. Without them, water would be a gas at room temperature.
Wow. So how do you rank them? If a molecule has multiple types, which one dominates?
The general rule of thumb is hydrogen bonding dipole dispersion. However, for very large molecules, the cumulative effect of many dispersion interactions can actually outweigh dipole forces, or even sometimes hydrogen bonding in smaller molecules.
The size matters a lot for dispersion.
It really does. So, first check for hydrogen bonding possibilities, H bonded to NOF. If yes, that's likely dominant unless the molecule is huge. If no H bonding, check if it's polar. If yes, dipole is important, along with dispersion. If it's nonpolar, only dispersion forces are present.
Okay, that framework helps. Now, armed with IMFs, let's look at liquids and solids again.
Yeah.
How do these forces explain their properties?
Right, let's take liquids. Their properties are heavily influenced by IMFs. Consider vapor pressure. In any liquid, some surface molecules have enough energy to escape into the gas phase. In a closed container, these gas molecules create a pressure above the liquid. If the IMFs are weak, it's easier for molecules to escape, so the vapor pressure is high. Stronger IMFs mean lower vapor pressure. And higher temperature always means higher vapor pressure because more molecules have escape energy.
Okay, and boiling point is related to that.
Directly. The boiling point is the temperature where the liquid's vapor pressure equals the surrounding atmospheric pressure. At that point, bubbles of vapor can form inside the liquid. The normal boiling point is just the boiling point specifically at 1 atm at pressure. Stronger IMFs mean higher boiling point because you need more heat to get the vapor pressure up to 1 atm.
Makes sense. What about viscosity? Like how thick a liquid is?
That's its resistance to flow. Stronger IMFs make it harder for molecules to slide past each other, so viscosity is higher. Think honey versus water. Temperature matters too. Heating usually lowers viscosity because the molecules have more energy to overcome the forces. Size and shape of molecules also play a role. It's super important in industry, like for oils, paints, food processing.
Yeah, I could see that. And surface tension, the skin on water.
Exactly. It's caused by the imbalance of forces at the surface. Molecules inside the liquid are pulled equally in all directions, but molecules at the surface are pulled inwards and sideways, not upwards. This creates a net inward pull, making the surface contract and act like a stretched membrane. It tries to minimize surface area, which is why droplets are spherical.
And that's why water striders can walk on water.
Yeah.
Their weight isn't enough to break that surface tension. Amazing.
It really is. It also causes capillary action liquids climbing up narrow tubes.
Okay, so IMFs really dictate liquid behavior. What about solids? The chapter mentioned different types.
Right. Solids are broadly classified by structure. Crystalline solids have that highly ordered, repeating 3D pattern, the lattice. Salt, sugar, metals, diamonds, they tend to have sharp, well-defined melting points. Their properties might differ depending on the direction you measure them, anisotropic.
And the opposite is amorphous solids.
Yes, like glass, plastic, rubber. Their particles are jumbled, disordered. They don't have sharp melting points. They soften over a temperature range. And their properties are usually the same in all directions, isotropic. For crystalline solids, the chapter introduces the unit cell. That's the smallest repeating box that builds up the entire crystal lattice when you stack it. It mentions different types like simple cubic, body-centered cubic, BCC, face-centered cubic, FCC. Just different ways the atoms or ions can be arranged in that box.
And the type of solid, ionic, molecular, metallic network depends on what the particles are and how they're held together, right? Which links back to bonding and IMFs.
Exactly. It all ties together.
So we have states, we have forces. How do we visualize how pressure and temperature control which state a substance is in?
That's where the phase diagram comes in. The chapter presents it as basically a map for a substance. It's a graph, usually pressure versus temperature, showing the specific conditions where the substance exists as a solid, liquid, or gas.
Okay, so reading the map, the lines on the diagram are boundaries.
Right. Each line, or curve, represents conditions where two phases are in equilibrium. The fusion curve is solid-liquid equilibrium, melting, freezing. The sublimation curve is solid gas. The vapor pressure curve is liquid gas, boiling, condensation.
And the areas between the lines are where only one phase is stable.
Precisely.
Yeah.
And there are a couple of special points. The triple point, point A, in the chapter's diagram, is unique. It's the one specific temperature and pressure where solid, liquid, and gas can all coexist in equilibrium.
All three at once.
And then there's the critical point, point B, which is at the upper end of the liquid-gas curve. Beyond the critical temperature and pressure, the distinction between liquid and gas disappears. You get a supercritical fluid.
Whoa! The chapter shows diagrams for SCO and water, and they look different.
They do. Water's solid-liquid line slopes backwards, negative slope, which is unusual. It reflects that ice is less dense than liquid water. Increasing pressure actually favors the denser liquid phase, making ice melt. For ACO-ERO, the triple point is above 1 atm pressure. So at normal atmospheric pressure, solid CO, dry ice, goes directly to gas at sublimes. You have to be at higher pressure to get liquid CO. These diagrams really capture the unique personality of each substance.
Wow. Okay, so this has been quite the journey. From gases where particles are mostly doing their own thing, governed by P, V, T, and N, to liquids and solids, where everything depends on how tightly those particles are clinging together via intermolecular forces, dispersion, dipole-dipole, hydrogen bonds. And it all gets mapped out on these phase diagrams, showing how temperature and pressure dictate the state of play.
It really hammers home how crucial those intermolecular forces are. They explain why things boil, melt, flow, or form crystals the way they do. Understanding IMFs unlocks the why behind so many physical properties we observe every day.
So, for everyone listening, think about something you see all the time. Water boiling on the stove.
Yeah.
Condensation on a cold drink can. Heck, even just the way honey slowly drizzles compared to water splashing. How do the ideas we talked about, particles arranging themselves, the forces pulling them together or letting them fly apart, explain what you're seeing? And maybe consider this, just how drastically can a simple change in temperature or pressure rearrange the whole structure of matter right in front of you? It's pretty profound when you think about it microscopically.